For my Engineering 350 Operations Research Final project, I selected an edible arrangements supply chain problem. With previous experience in supply chain, I was assigned the task of minimizing supply chain costs, specifically during the month of February, which is one of the busiest times of year for the company. I will attempt to solve this problem again using new techniques and technology from operations research, including constraint programming in CPLEX and a simulated annealing algorithm using VBA. There are 5 different basket types that are produced during the month of February, and there are 8 different produce items that need to be bought to use in each basket. The produce items include pineapple, strawberries, bananas, apples, grapes, milk chocolate, dark chocolate, and white chocolate. There are 3 workers available, Alex, Anna, and Abby, who are in charge of assembling the 5 different baskets. The objective is to determine which task should be completed by which worker, based on worker and time constraints, the sequence each basket should follow through the stations, and how long each basket will stay at each station. This will all be included in solving the overarching optimization problem of determining the minimum supply chain cost for the month of February at Edible Arrangements. There are many constraints for this problem. To begin, there need to be enough supplies purchased to make 5,000 of basket 1, 2,300 of basket 2, 700 of basket 3, 8,000 of basket 4, and 890 of basket 5. All workers must contribute to each basket, and we must consider specific worker constraints, as Alex is the fastest at strawberries and pineapple, Anna is the fastest at grapes and apples, and Abby is the best at melting dipping chocolate. However, she often makes mistakes for rushing, and for every mistake made, there are redip or rework cost penalties. There must be end before start constraints for precedence constraints on produce, such as pineapple has to be completed before strawberries and bananas can begin, and strawberries must finish before bananas. There also must be no overlap constraints for all of the workers because they cannot be working on 2 things at once and must account for transition times between stations, as well as span constraints to ensure that the first basket types start with the first produce type and then the baskets span the produce interval to synchronize the 2. Finally, different sequence intervals should be compared to determine the best by making sure that shortest processing times are selected to minimize time and therefore total cost. The original CPLEX code that I used and edited is the scheduling sequence sample project. This problem involves building 5 houses in different locations with different tasks, such as masonry, roofing, and painting to be scheduled. To tailor this code to the supply chain problem, I added multiple cost arrays and created the objective function to minimize cost, while taking into account how many of each basket is made, and also rework costs. I added precedence constraints for each produce type for the end before start constraint to make sure certain produce types were completed before others could begin. Then, I changed the span constraint and the no overlap constraint that were already included to make sure workers did not overlap jobs and account for transition times as well. I changed the tuples to make the sequence output precedences and basket sequences with the times at each station to select the minimum sequence. We also assume 5% of the total number of each basket will need rework. The outputs for the cost minimization and sequencing problem include a total cost value representing the current optimal solution found for edible arrangement supply chain, the decision variable called intervals, which outputs 8 sequences, 1 for each produce type. The 5 values in each of the 8 interval sequences represent times at each produce station for that produce type job to be completed. The 5 intervals, each including 8 sequences within the interval, are output for the total of 5 different basket types that are being produced for the month of February. Decision variable interval basks includes all of the 5 basket types in the interval. It outputs an array of 5 sequences, 1 for each basket, with the chosen sequence for each basket showing the order and how long each station lasts for that basket. Then, the decision variable sequence called workers outputs a sequence with an interval for each worker in the worker named array at each produce type station. This shows the times and seconds that it would take the corresponding worker to complete each produce task for the corresponding basket. That is why each worker has 5 different sequences output with their corresponding value. These sequences are used to select the minimum by taking the sequences with the best times for each worker to make sure all needed tasks are completed by a worker for each basket. Finally, the most important output is the objective function value. This determines that the minimum supply chain cost for the cost of all supplies for 5 baskets during the month of February is $473,176.50. A simulated annealing algorithm was created using VBA to search for a feasible cost solution. The cells for different produce types for each basket are set, and there is a location for the current solution and the best minimum value. Random numbers are generated within a predetermined range, based on how many of each basket type is needed and how many of each produce type is needed per basket. There is a constraint that ensures that we do not exceed the maximum number of baskets needed. Then we begin the annealing process. When the value of the constraint is less than or equal to 16,890, which is the maximum allowed value, we randomly generate a number to test against and solve for z. This is e to the negative value of the best minus the neighbor or current solution, divided by temp. If the current is less than the best minimum, the current value replaces the best and becomes the new best solution. We continue to loop, and each iteration takes the temp value and divides it by 2. The best feasible solution I have found using the simulated annealing process is $616,645.40, which is off from the Cplex solution because simulated annealing does not always find optimal. While the results using Cplex are much better than those found using simulated annealing, it is expected that the simulated annealing solution will not be optimal because a random initial solution is generated by exploring a small neighborhood of the feasible region, and therefore it finds local feasible solutions.